you have a spring with a constant of K of 170 newtons per meter, and I have a frictionless incline. And it says that the angle is at 37 degrees. So what I want to do here is that when I look at this thing here, I want to find out what's in my system. Okay, what's in my system? Do I know what my system is? Well, when I look at my system, just by looking at the picture, and the key word for me was this right here, frictionless. So that means here is that if I look at, so what's my system? Well, in this case, I have an incline, which I already said here is connected to what? Earth. So right away, I could come in here and go like, okay, I have the Earth here. And in this scenario here, you see that I have a spring. So the fact that this guy here has mu equal to 0 means that if I isolate my spring and the Earth, then I can see here that there's only two possible forces. There's this force, the force of gravity, and then there's this force, which is the spring force. There's no other force in the system. So immediately what this tells me here is that E mechanical is equal to a constant. I can apply conservation of energy. So now that I can apply conservation of energy, I know that the only thing that I know here is that the spring potential, gravitational potential, kinetic energy are going to interchange amongst themselves. And as they, interchange, they will adjust themselves to keep mechanical energy a constant throughout the motion. So let's go read the rest of the problem now. So I know that for a fact. So it says at the lower end of the incline is a distance d. From the end of the spring, which is at its relaxed length. So in other words, if I look at that, just alone that statement, I think I'm going to have to draw a big picture here. Yeah, so let's draw this nice and big so that I can spread it out. So here's my incline. I know that this is at 37 degrees. So let's look at this. So I'm going to take my spring and I'm going to compress it to 20 centimeters from its relaxed length. So let's do this. So let's say that this is the relaxed length right here. So this is the point where I have x equilibrium equal to 0. And then what I'm going to do here is that I'm going to compress the spring 20 centimeters. So let's say that this is my block right here, and I've compressed this thing so that the distance from here to here, right? So how do I write my distance here? So I know that this compression here from here to here is 0.20 meters. That's my compression distance. So then it says that I take a canister, I push it against the spring until the spring is compressed 0.2 meters and it's released from rest. So I know from right here, I know that this guy right here tells me that it's at rest, right? Clearly the velocity is 0. I know I compressed this thing 0.2 meters. So what that means, I have to know its height. So I know its height here. This is known. So, but I'm going to have to calculate that. So look at that. I know velocity. I know the height, and I know the compression is this. So therefore, this is my known energy state. I know the velocity, the height, and the position. So then the question is, what is the speed, right? That's the question. What is the speed when it returns to what? Its relaxed length. In other words, the equilibrium. So then the block is going to come all the way to right here. Okay? It's going to come to right here. And when it comes to right here, our question then is to do what? Figure out what its speed is at that point. And so because I don't know the speed, that's going to be my energy state 2. And the only thing I know is that from the bottom, this is 2 meters. Now, I don't think we need that right now. I might adjust it for a minute, but I think I'm going to leave it right there. So then, now I'm going to start my process here. So what's my process here? I know that E mechanical, right? I know that E mechanical is a constant. If it's a constant, I know it's got to look like this here. And I know that this guy has to be a constant. So if this guy is a constant, we don't care about that. Pretty soon I'm not going to draw mechanical energy, but what do I know here? Well, when I look at energy state 1, right? Energy state 1 tells me what? There's a height change and a compression. But V is equal to 0. So I don't have any kinetic energy. So this tells me here is that part of this piece has to be what? Part of this guy has to be gravitational potential energy. Part of this has to be spring potential energy because of the compression. So when the block slides all the way down, and when the block gets to the equilibrium point, the spring force is 0. So at point 2, we see here is that the spring is at equilibrium. So I have no spring potential energy. And if I choose my reference potential to be 0 at this point, then I'm going to say here is that now I have no height change. Then that tells me that all of that must be in the form of kinetic energy. So then, according to conservation of energy, it tells me that this must all be kinetic energy at 2. So what does conservation of energy tell me here? Conservation of energy then comes in and just says, okay, my known energy versus my unknown energy looks something like this. So if you go and you do it by the textbook, then you should be writing this thing right here. And that might work for you. And I applaud you if it does. And if you do this, like this, then you know it's this. So then you got to go and determine it. Or you can draw a picture. And if I draw a picture, I immediately see that the kinetic energy is 0 right from the get-go. And when I get all the way down to the bottom, I see that this is 0, this is 0. So what I'm really writing here is that I'm writing UG1 plus UGS1, which is K2, and you could see that's exactly my picture right there. So according to conservation of energy here, what I'm really seeing here, mathematically here, is that I have this equation. I have mgy1 plus 1/2 kx1 squared equals to 1/2 mv2 squared. And clearly, this guy right here is my unknown. That's what conservation of energy tells you. But remember what I said. The hard part is now getting these details. Okay? Getting these details. So what are the details here now? So the details look something like this. What we got to do here is that we got to go solve for these things. So the first thing that we see here is that we know that there's a compression. Okay? So we know there is a compression. And so when you think about this, note that we're really setting up a triangle. If you look at the triangle that I want you to pay attention to is this triangle right in here. So what I really want you to look at is this triangle right in here. And if you look at that triangle, actually that's not the triangle, my bad. Because that includes past the compression. It's really this triangle right in here. And if you look at that triangle, what's really happening? That triangle says that it looks like this. This is 37 degrees. Now let's be careful. This is the distance here. That's the compression. This location here is my equilibrium point, and now I compress the spring. How much did I compress the spring? Well, I compressed it a distance of 1 equal to 0.20 meters. So that means as I compress it, what ends up happening is that I now increase the height by a height of y1. So now I got to go get y1 because you could see I need y1 right there. So here I go. So then what I'm going to do here is that I'm going to use trig, which tells me then, you could see that the angle is what? Is going to be the opposite. So if it's the opposite, it's got to be y1 over x1 should be the sine of 37 degrees, which then tells me here that y1 is then x1 sine of 37. So I now know what that value is. So I know the height increase, I know the compression, K and M are given. I could now go in and plug this into conservation of energy here. So let me go do that now. So what I'm going to do here is that I'm going to come in is that, so now from conservation of energy, where's my mouse? There it is. So from conservation of energy, what do I have here? Well, I have mgy1 plus 1/2 k x1 squared equals 1/2 mv2 squared. I need to solve for v1. So not v1, solving for v2, then you could see here is that v2 then, if you look at that, I already have the right side, excuse me, the left side, so I'm going to write mg y1 plus 1/2 k x1 squared. And then you could see on the right side, I have 1/2 m, so I'm going to divide this by 1/2 m, then I have the square root. So if I look at this thing, I could now plug in certain values, right? I know that y1 is going to be, I didn't calculate this thing. I just put this all into my calculator at once. I know that x1 is 0.20 meters. I know that the mass tells us in the problem that it's 2 kilograms and that the spring constant given in the problem is 170 newtons per meter. So if you punch all of these numbers in, I now have a speed of 2.40 meters per second, and this is velocity 2. And now I have my speed through conservation of energy. So let's set up the second piece before we leave and then come and look at this thing. So now we're on B. So when you look at B, we're looking at this guy now. And what we want to do here is that we want to know what the speed of the canister is when it reaches the lower end of the incline. So how do I do that? Well, I'm still good. Note that we've already solved for the speed once. So what we want to do here is that we want to adjust our picture here. And there's lots of ways to do this. The most common way is that we change how we look at potential energy. So what I'm going to do here is that I'm going to draw two pictures. So I want to draw two situations with energy bar diagrams. Okay, so the first picture is that I want to stay with the same picture that we had. Okay, so if I stay with the same picture, let's draw my incline. So I have my incline here. And when I look at this incline, what we did here is that we compressed the spring. This is where the block started. And this is what we called energy state number 1. And then what it did here, the block went to the equilibrium point. Right? So right here, what we know here is that the block is moving at number 2. And what we're really interested is what is it doing down here at the bottom? And then here, I think the notation really starts to pay off because now we're really looking at state number 3 here. So at state number 1, we knew that it started from this height right here. And this is the height that we called Y1. And of course, when we're looking at this thing here, when this is here, we know that it has some kinetic energy, which is moving in this direction right here. Right? We know it has kinetic energy right there. So the question is, at this point, we defined that Y2 here was equal to 0. That's one picture that we can do. So we can keep our Y2 equal to 0 there. And what we find here is that this bar diagram is somewhat more challenging, but I want to look at a different picture here. Now imagine that I have the same scenario here. Okay, so I'm going to copy this just for being fast for the moment because I got to stop here very soon. And here's what I want you to think about. Now suppose that I have the exact same situation, but this time what we're going to do different is that we're going to take away our y equal to 0 there. And what we'll do here is that we'll adjust our y3 to be 0 down here. So what this does here is it actually changes our reference. So here, what we're seeing here is that there's a change in reference potential. And you'll see that by changing the reference potential, it actually makes the problem a little bit easier. But I think we should draw both of the diagrams so that you can judge to see what works best for you. What we did beforehand is that we started with energy state 1, we went down to energy state 2, and at energy state 2 was the equilibrium height. And then we determined what the speed was, or we now know what the kinetic energy at point 2 is. Now I could continue along this point where I set up y here, y2 equal to 0. But note that if I set y2 equal to 0, then that means the block is going to slide all the way down to the incline here. And what our job is to do here is that we want to figure out what is the speed v3 right here is. So the really important thing for you to think about is that note that means that the distance that you go from state number 2 to state number 3, this distance from here to here, I would call that y3. This is a negative number. And because it's negative, that means its potential energy is negative. And we'll look at that in a moment here. The other thing that we can do here is that we could change our reference potential. And if we change our reference potential, which we're over here, remember, we're still trying to calculate the speed of the block coming down right here. The more common thing is to change our 0 from position 2 down to 3. And if you do that, what that tells you here is that look at what this height is right here. Let me change color here. Look at what this height is now. In this case, the height here, which is what I would call y2, is positive. So this tells me that I have a positive potential energy. So what I want to do here is that I want to draw a bar diagram to give you a sense of what I'm talking about. Okay? And this is what we're really saying here. Well, what we're saying here is that we're saying this, is that I'm going to look at the energy graphs of point 2. Okay? And what I'm seeing here is that starting at point 2, the bar diagram looks like as follows here. And remember, the bar diagram is important because why? It tells us that how to write down the equation. So if I look at point 2 here, when I look at point 2, what am I actually seeing here? Well, I'm seeing that I have a certain amount of kinetic energy. Okay, so when I look at this kinetic energy, what am I seeing here? Well, I'm going to say that this is point 2 right here. I have this amount of kinetic energy. But note, at this point here, I have 0 gravitational energy. So at that point, I could see here that my total energy of the system looks like this here. But if I compare 2 to 3, note that the speed at 3 must be higher than the speed at 2. Because why? It's sliding down the incline. Of course, it's going to be going faster. So what that means here is that when I get there, I'm going to have a higher kinetic energy. So note, so this is the important point right here. Note that this goes over, so remember this is a constant. So that means that this goes over the total energy. So does this violate conservation of energy? The answer is no. Remember that y is negative and potential energy is proportional to y. So now gravity, if this is how much it goes above it, gravity is then below it by that amount. So now I have a negative gravitational potential at point 3. Now note, this riles some people up. So when I add kinetic 3, K3 plus UG3, the total is still equal to the energy situation. I have not violated conservation of energy. On the other hand, we could do the following thing. We could come over here again starting from 2, from point 2, the bar diagram looks like what? Well, in this case here, note that there is potential energy at point 2 because our reference now is this Y3. That's where the zero potential energy is at. So when I'm looking at this thing here, here's what I'm going to find. Well, I'm going to have, so if I look at how much kinetic energy I have too, it's got to be this right here, right? Oops, wrong color. So if I look at point 2, I'm going to say, okay, this is how much kinetic energy I have right here. That doesn't change because the speed is the same. So note that the kinetic energy on the left and the kinetic energy on the right are exactly the same. The difference is what? There's now a height change. So when I look at the gravitational potential here, let's say it's this big, at point 2, you could see that this is not 0 anymore relative to our 3 here. So when I'm looking at this, you could see that they have 2 different potentials, but they have the same kinetic energy. But now conservation of energy tells me what? This is my constant. I can't have more energy than this. And so here's our state 2, but now what happens? This thing slides all the way down. And as it slides all the way down, that kinetic energy should be the same as K3. And I'm saying, did I draw that too big? I'm hoping that they're about the same size. This would be kinetic energy 3. So the question is, which is easy for you to understand? If you like the left one, you should use that one. If you like the right one, you should do that one. So what I'm going to do here is I'm going to change what I'm doing, and I'm going to do the following thing here. I'm going to say I'm going to use the left one, the right one, because that's the more common way to do that. And so again, this is where Y3 is equal to 0, which tells us that the potential energy at Y3 is 0 here. So I'm going to use the right picture here. So I'm going to use this right bar diagram to write my equation. So what do I see here? Well, according to conservation of energy, at 2, it must be the conservation. You know what? I want to do this here. Everything is known about 2. What's unknown about 3 is its velocity. So when I look at my equation, I'm going to write, well, that's what I'm going to write here. And then this guy should equal the kinetic energy at 3. So when I write this detail down, what I got to do here is that I have to do what? This is going to be mg y2 plus 1/2 mv2 squared, and this is going to be 1/2 mv3 squared. So what I'm seeing here is that we've already calculated this. We said that V2 was equal to 2.4 meters per second. This guy is the unknown, and we don't know the height Y2. So this guy we have to calculate. So let's go do that. So the way we'll calculate it is that we need to set up a triangle. So we know that this height right here is Y2, and this is what we're after. We know the angle. They tell us that the angle is 37 degrees. And when we go right up back to the problem here, look what it says right here. It says that the lower end of the incline is a distance d 1 meter from the end of the spring. In other words, this is d to the equilibrium point. And this point was our point number 2. This is our point number 3. So I know that d is 1 meter. That's what we got to pay attention to. So if d is 1 meter, then that means I know this distance is 1 meter. So now I have the ability to solve for y2. And what we're seeing here is that y2 over d should be the sine of 37, since it's the opposite angle. So therefore, y2 should be 1 meter. Actually, I didn't calculate this number, so I'm just going to leave it as d. I only calculated this thing at the end. So I'll write that as d, and when I go and I do my final answer, we'll replace that with 1 meter. So now I know everything. I know the height, I know the speed, I can calculate v3. So here I go. Solving for v3 using conservation of energy. You could see here is that, look what I got to do here. I'm going to divide everything by 1/2 m, and then I'm going to take the square root. So I'm going to get mg y2 plus 1/2 mv2 squared divided by 1/2 m square root, and then this is v3. So if I start putting stuff in here, note that I can immediately cancel all the masses out. That's a nice feature. And then look at my y2. So this should be gd sine of 37 plus 1/2 v2 squared divided by 1/2 square root. And then I know that d is 1 meter. I know that v2 is 2.4 meters per second. And if I punch that into my calculator, I get a value of 4.19 meters per second for v3. That's conservation of energy. So we want to now go to the next example and keep moving along this direction here. So this is a more involved example. Okay.